Hold on, guys, just 1 or 2 minutes. We'll be starting. Can anyone record the meeting for me? Uh, Hello. Yeah, that will be helpful. Okay, let me know when to start. Okay, fine. So we'll be having, so the session will be organized like this. We'll be briefly going over linear regression, then classification. So these are the two basic machine learning tasks, and maybe we'll look at how to implement them from NumPy and other libraries as well. We'll go how to implement a softmax classifier in PyTorch. Now, PyTorch implementation is very handy and helpful. So, and after that, we'll discuss some elementary aspects of active learning. So, okay. Uh, so this is the first link that I shared regarding the linear regression. What linear regression is basically means that you fit a line for all the data points, and how it works is uh, so it's something like the average of something, that you have a data point and this is the prediction, and you essentially compute the different square of the error term, and then you normalize it with 1 upon n. So this is the better explanation, I think. Yeah. So what happens is that you assume that you come up with some parameters, and then you assume that there is a linear relationship, and using them you predict some value y. So x is the cumulative vector which contains our features, and theta is the model weights. So h of x, which means you compute something using x, yeah, and then you have the difference with it with the y values, the uh, the value which you want to compute, and then you take a square of those values, and this 1 upon m is the normalizing factor. So the screen is visible, right? Hello. Okay. So this is essentially linear regression. You must have done this in uh, linear algebra, and so we'll going over this medium pose. So it tells how to implement. So we import the libraries and do, this is just looking over the data and feature normalization. So one thing is that feature normalization is really helpful, because suppose there is some value which are -100, some values are 100, so the computation is not very efficient. And so we what we do is we make all the values between uh, 0 and 1. So or rather minus, between minus yeah. So we normalize those values, we subtract the mean and from the values, and we divide it by the range. So the mean shift to 0 and the range is also shrunk to, so I think, okay, sorry, we divided by range by 2. Yeah, so mean shifts to 0, and that, so that is the feature normalization. And this is the plot of the data. Hypothesis is something that we assume that the model depends on these x naught and x1 parameters with weights as theta naught and theta 1. So hx is theta transpose x. This is a linear relationship that we come up with. We can also come up with, so this is essentially feature engineering. You find out what features are important. Suppose we can say that there are three features: x naught, x1, and x square. That is also perfectly fine. So you can have any features for this. And in machine learning, we optimize with a we have a cost function. So okay, so in machine learning we have a few things. What we have is the data. Then we have the hypo hypothesis, which means that how will we, or essentially hypothesis is how we feel that the data might depend on the model, or how the output can be computed using the relationship between model and the data that will lead us to the output. That is hypothesis. Then we have training objective. So this is something that we train on. This is the loss that we want to minimize. Then we have okay, so this is the training objective which we come up with. Using training objective, we come up with a loss function. Loss function is that we want to minimize a loss function. And then we have an optimizer. Optimizer is okay. Before optimizer, we have a gradient descent, or an algorithm, say, which will help us compute these to the optimizer and then backpropagate. So I'll explain these things. Uh, Data is clear, like the data we get. Hypothesis is some rule that we come up with to like fit the data. Training objective is uh, some function on which we like which some function which we want to optimize. For example, we can say that in least square regression, we want to optimize this the square difference between predicted and the actual label or actual value. So this is the training objective. Now loss function, we come up we from training objective we derive a loss function. Loss function is basically the function which we will minimize, the exact mathematical representation which we will minimize. And then we use gradient descent. Gradient descent is basically is gradient descent is like is one of the algorithms which we use to achieve where we want to go. So essentially, gradient is the direction of the steepest ascent. If you plot the data in a higher dimensional space, then gradient points to the direction which is most steep and increases. So essentially, we if we go in the opposite direction of the gradient, we will reach a minimum or a local point which is the minima. And so we compute the gradient of the loss and we move in that direction. So yeah, so that is gradient descent. We compute the gradient and we slowly move in that direction. And back propagation, back propagation is basically is used to update the model. So what happens is, suppose there is a curve y is equal to x square. Should be something to draw. Okay. Oh yeah. So to put it simply, suppose we have a curve, we plot the data. The data is on this manifold. Manifold means a surface which separates data points from non-data points. And we have a data on this. And no, sorry. How to this? R. Hmm. Yeah. So this is the graph of a loss function. I should explain it like this. This is a graph of our loss function, and we are suppose somewhat here at this point. Then what will the gradient will point in this direction. So we will move in the direction opposite to the gradient. That is the line of the slope, or the line will move opposite to where the steepest ascent is. Then we come up. Then we slowly we update the model, and yeah, so that is back progression. But why do we move in the direction of gradient? That's because we want to reach the minima. This is the graph of the loss function. We kind of find the local minima in the we want to find the global minima actually, but we have an algorithm gradient descent which will find us the local minima, and that's why we use gradient descent. Gradient descent means that in small steps we will go in the direction, like here the gradient was this direction. At this point the gradient will point in this direction, so we'll move opposite to this and reach here, and so on. We will move in as per the gradient and will reach the minima point. So this is gradient descent. And uh, so gradient descent, and what are other things? Yeah, so gradient descent is used to optimize the loss function or come up with the minimum value. Back propagation is basically in the process we will update the model. We will make changes to the model so that model helps us come up with the proper like proper weights. The theta in this example, theta and theta naught and theta 1 are the weights for the model. So we'll come up with proper weights. And yeah, so this is backpropagation gradient descent optimizer. Optimizer is something which is used to quickly or optimize the process of gradient descent. The algorithm which we use find the loss, we use optimizer to optimize that. So these are the some basic aspects while writing the model. And now back to this. So yeah, this is the cost function actually. So that's I wanted to explain linear regression and the cost function. Cost function is basically this cost function we use in linear regression. And appendix is not. So this is the code for that we initialize the parameters and we fit the best fit line such that the sum of the least square distances is minimum. And yeah, this is the gradient descent process. We compute the gradient, and with a step size we move in direction opposite to the gradient and update it. So this is gradient descent. Okay. And we optimize it. Okay, so this is the NumPy implement. Linear regression is very easy to implement, but I share this NumPy so that you guys can get a feel of what actually happens intuitively when we fit the line or in any machine learning in general. So now we plotted this best fit line, and using this line we can extrapolate the values. For example, if for something we need to find a value, we can extrapolate using the best fit line. So this is the basics about linear regression. I shared a scikit implementation also. So that will tell how to simply implement the linear regression. Hypothesis, cost function, gradient descent. Hypothesis, like I can go ahead and explain if that the previous explanation was not helpful. Hypothesis is the equation that we come up and using the models other than the features. For example, x is a feature, it's an 1D, and also there's a constant term. We also this constant add this constant term. This is kind of a bias term, you can say. Or in terms of uh, boundary, we can say how much push we want to, how much we want the plane to be shifted away from the origin, because this represents a equation in a plane. That is something along these lines is a SVM. But okay, this is the cost function. Cost function is the function that we will use to optimize. We'll optimize over it. And gradient, yeah. So this is gradient descent. And alpha is a learning rate means suppose we want to go in a direction. If we go very fast, we can go very slowly. So that is gradient descent. And the post also shares how to choose alpha. Initially, if we choose very large alpha, then we will overshoot, we will miss the minima. And if we choose small alpha, that will take a lot of time. So alpha can be optimum based on the previous experiences, or it can be adaptive. Adaptive means we change the alpha. And I think this is all I've already explained. Scikit-learn, yeah, scikit-learn is like very easy to implement. You load the data set, and this is the data set. Okay. So this function is very useful. It's elsewhere also. Train test split. You split the data set into train test, and test size. This is the fraction what will be go to test, and random is the seed. And this function is very important. And linear regression. Yeah. So this is like LR.fit. You get a model and you fit this X train and XY train. So all of the entire computation that we did in this post is like all this gradient cost and all and fitting. This is very easily done this using this fit function. So it's helpful to keep this in mind. This like these two posts are very good to understand linear regression. I have just rushed over this concept, and if there is any doubt, I'll be happy to take them towards the end of the lecture. Now let's go to classification. Uh, classification. So linear regression is basically when we want to fit a line. So there's a data, we want to extrapolate numerical values. Classification is we want to the bucket the data set into aspects. Like suppose there's a images, we have the images, and we want to say if these images belong to cat, dog. So that is a simple binary classification. Okay. Uh, then classification includes feature extraction, which means preparing the right data set and features and all. And this is feature abstraction and plotting. ANN implementation. So, were you guys able to understand like this neural networks? Neural networks is basically okay. Let me go over it briefly. What is ANN? Uh, ANN is simply okay. Uh, in ANN is a group of linear classifiers which in very vague terms, because what happens in linear classifier is you add in term you can represent the linear classification in terms of this linear regression in terms of this wx plus b. You fitting a line based on the features. These are matrices, bias vector, x vector matrix. And classification is you add an activation function to this. So this is simple neural network. What happens is that you uh, you take the linear input of all the features, and then you apply some kind of a non-linear function to it and get the output. So this is one node in that, and there are several uh, you can say nodes in the layer, which each of them does this. You get a single value out of this. So this makes one layer of the ANN, or of the neural network. And similarly, there are several layers stacked. And at the end of it, you get a vector. Vector means, how do you get a vector? This will return a one value. For each of the uh, nodes in a layer, you get similar function. You just stack them up as a vector. So that's how you get a linear ANN. So which means that you take x1 is the first value, you pass it to the input. Then suppose we are considering this node, this gets values from all the vectors. So it's like multiplying all of these with some constant, adding them up, we come up with something, and then we use activation function to scale that value to come up with something meaningful, and then get an output of this. So in like we stack all these values, we get a vector. So that is ANN function. Sorry, that is a output, and we can stack this up, like repeat this process. So we get layers, input layer, output layer, hidden layers, and I think this would have been a little bit tricky to understand. Okay, so now so why do we need this activation function? We need this activation function to learn non-linear like dependencies, because what will happen, suppose there was one layer which is only linear, then the output of that say we call it y, then what in the second layer what we do is we do wy plus b2. So like this essentially is a waste of the like a compute and all this also, because it's just a linear relation. We can substitute y from the above. So z is equal to w2 w1 x plus b1. So this rearranges to w2 w1 x plus w uh, 2b2 plus b1. So this is simple linear regression problem. So that's why we add, to learn complex things, we add this activation function. This also helps us to like scale the values and all those. So this is what we can say is ANN. And finally, usually what we do is we use some other activation function. Okay, this is done. Some other activation function in the header layer, and in the last layer we use softmax. Softmax is a way to compute, is one of the ways from which we can get probability representation from the actual values. So softmax value is between 0 and 1, and it is computed like, softmax is computed like, suppose we have a vector of x, a, b, c. Softmax will be exponentiating all these c and computing the sum, and then the vector of softmax vector will be exponential of a divided by sum. So that will be softmax, and sum will be sum xp. So that is the softmax. So we compute softmax. Softmax is actually sum of the we exponentiate everything, compute the sum, and then we normalize it so that it remains between 0 and 1. This is always positive, so it will remain, it will not be negative. Uh, that's that. So we can take soft. It's usually convenient to take softmax as probability representations. So when we do from the last layer, we will get a representation. or probability distribution, and usually the number of nodes in the last layer is equal to the number of classes, or number of classes plus one. Then we can say that we cannot classify. So what do I mean by that is, suppose the classes are cat, dog, unclassified. So there can be unclassified. So these are three classes. Otherwise, we can have cat and dog. So these are the two classes. So we'll have three nodes in this and two nodes in this, representing the probability that the input belong to cat, belong to dog, belong to unclassified, or belong to cat, belong to dog. So this is how, okay, we can use a simple neural network to get a classifier. Now this is, I think, you load the data set, you get the features, and this is the NumPy representation of the neural network, which is you get the input weights as uniform weights from a uniform distribution. Like initially, you have to initialize the model with something, so you're initializing it with random variables, and this is computing the output with these random classes. Then what we do is we define the network. The sigmoid is the activation function. It is like I have told you. And okay, so ReLU is also one of the activation functions. It goes like this. Okay, I can show you with a graph. ReLU is like this. For negative, it is 0, and for positive, it is x. So max of 0 and comma x. And this is usually we use ReLU or tanh. Tanh is hyperbolic tanh. You can Google that function. We use those two functions usually in the middle layers or the hidden layers. Okay, where it is. So this is the sigma. These are the activation function. This is the function for updating weights. How do we update weights? We use initial weights minus learning rate into weights. So essentially we are doing just this. The initial model weight vector minus learning weight into the gradient of the loss function. Okay, so this is how we can like update the weights. Okay. And train network is basically defining how to train the network. Train networks means where we go over all the data points and we compute the values, or like compute as per that. Okay, we go over all the data points and pass them to the neural network, which means we apply the matrix multiplication, and then we come activation, matrix multiplication, activation, and we can see that activation is ReLU. Okay, so okay, yeah, and we return the weights and predict output. So yes, and so we pass it, we train the network, we predict output. Predict output is very simple. We just don't do any back propagation or computing. We just pass the data as it is. We just pass the data and predicted label. Okay, so how do we compute the predicted label? Now, suppose I call this vector softmax vector as x, y, z. So these represent probability distributions, which means that the sum of these values will be 1. And the class which I should take is a very simple way to take all the classes is to take the maximum value of this. Suppose this vector is the softmax vector is x, y, z. So if the maximum value of these three things will be x, which means that it belongs to cat. If it belongs to z, it means it is unclassified, or it belongs to something else. So we can say that the maximum value represents the class, and that is what is done here. Yeah, yeah, here. So R1 is equal to numpy dot max R1, which finds the value where numpy is maximum, like the maximum value and the corresponding label to it. And we return the label. And this is the uh, basic idea about the classification. Uh, this was implemented using NumPy. Now, for the our purpose, what we'll be going for the active learning, we will be going forward with classifier, and we are only concerned with PyTorch implementation. Like all the things, all the loops and all those can be helpful, like can be done in PyTorch, and is very useful to learn. So we're dealing with how to like develop a PyTorch classifier. So this is essentially loading the libraries. We PyTorch, we import it using torch, and torch.nn means neural network. Optim is the optimizer package. Functional means to pass some values. Essentially, function has some function, and we use it for softmax. F.softmax here. So train loader, for data loader, we pass the data to a model using data loader, and defining the softmax classifier. This is the machine learning model actually. We define models like this. We develop a class and make it a subclass of the NN module. And there are some methods like def initx forward. Forward means how to compute. And there is also a get item method. Get item. Mm, uh, get item method. Yeah. So init is to like initialize. This is something like the constructor in C++. We initialize it using the superclass, as well as linear. We simply make uh, a linear layer. Then forward means to like how should the data be handled if it is passed to this model. We'll compute the softmax of the linear layer. So this is just one linear layer, and dimension is equal to one along one dimension, which means along the column. So we'll pass the data as a group, which we'll call a batch. So I'll be going over that also. And get item means that if we pass an index to it, suppose we want to know the fifth, so it will return the fifth item. So this is how we develop a basic a model in this PyTorch. Then we create a sample data set of 1,000 size and 10 features. Then we assign them features using random, and we create a data set. Data set is basically we make a tensor data set which is suitable for PyTorch, and then we use a data loader to convert the data set. Like in PyTorch, we pass the data using a data loader. Uh, so that is the data loader. And batch size 32. What is batch size? Batch size, which means that suppose we have a data vector, we can we okay. How to say this? Suppose we have three vectors in our data set: zero point 0.5, comma 0.2, comma 0.3. Hmm. Now we can pass all of these. We have to train in a these are in a training set. So we have one sub all the data. We basically divide into some parts. The most common division is that we divide into two parts: training and test. So one which we'll use to train the model, and for some which we'll use to test the model. It's like we have some question bank, and we'll give some questions to the student as an assignment to for him to learn, majority of them usually, and we'll use reserve some questions for him to ask in the exam. So this is like that. And this is, I think, what will be 4, 0.3, 0.7. So these are the three vectors that we're having. Now, what we'll do, our model will go over each of them. Train, train means like compute gradients, back propagate, and so on. Compute gradients, learn the model, and so on. So the thing is that what we can do is we can pass all of them together like this as a matrix. So it will take, say, bunch of data points at one go, rest of them at another go, and so on. So this is the collection that we pass is known as a batch. So which here we define batch size 32, which means that we'll passing 32 points at once. Shuffle it equal to true, which means that we can rearrange the order of these rows in the matrix. Uh, so we'll come up with a data loader. Now model, like we have to initialize the model. This is something like making an object from a class. So we make a model object. Criteria is cross entropy. Cross entropy is the loss that we use in classification. Uh, I'll go over cross entropy loss also. Cross entropy is uh, okay, and we'll go over optimizer. Optimizer is optimal SGD. SGD is stochastic gradient descent, which means that we will take like it is gradient descent, but instead of like taking all of the values, we just take gradient along random direction. And learning rate is the alpha that we saw. I think I should go over it. Like cross entropy loss and okay. Uh, Cross entropy will like should take some time to explain, but I'll attach resources to this. There are some laws. Stochastic gradient descent is simple. We compute gradient with respect to model, and for stochastic gradient descent, we need to uh, random. Like we'll choose random direction. Suppose we have data. Okay, let's go like this. Uh, Suppose we represent our data on a multi-dimension space, and here there are only three spaces, so we can have three axes, x, y, z. And what we can do is when we compute gradient, the gradient will be of the form that uh, del by del x, del by del y, del by del z, so on. So instead of computing all of these, we can compute along random directions, say 5 or 2. Like we can have to specify how many we want to choose. I think it's usually done for the one. Picks, like usually it is one, picks one data point from the whole data set to computation. So like it's just like that. Here we have computing for three. If there is f feature, if there are if there are 100 features, then we'll compute for 100 times this value and do back propagation and all those things. We can take this only one direction. For example, y. Rest of the thing will compute. We'll assume that it is not changing. So we'll move along only y direction in the data space. Uh, okay, so that was where are we? I think here. No, SGD and uh, cross entropy loss is hmm, cross entropy. Like it will take time to explain. There are various loss functions, hinge loss. Let me see if I can find an easier explanation for that. Cross entropy is basically uh, P log Q. Mm, True probability and yeah. So cross entropy is basically this thing. You have a true probability distribution and you model this is the predicted distribution. You compute this and you want to minimize this as a loss function. So there are various loss, and cross entropy is one of the most popular loss functions. You can go and read about this uh, for the intuition of this. It essentially wants to minimize the difference between two distributions. There are other losses also. I'll attach this to the Discord. Hmm. So okay, so we compute the optimizer, then we'll train the model. For training, there's a number of epochs. Number of epochs, which epoch means how many times the model sees the entire data set. So 5 epoch, and then we'll go over each batch in the data loader. We offset optimizer to 0 graph. We reset the optimizer. We compute outputs, and then we compute loss based on the output and target, and then we loss dot backward. Loss dot backward means okay. So PyTorch, in like you can see PyTorch is very helpful because in the in the original thing that we implemented, we saw that we had to implement gradient step. But in the PyTorch, but in this thing, uh, there's a gradient tape. Gradient tape is basically a graph which computes all the operations that are performed, and it is automatically computes the gradient when we do this optimizer dot step. So loss dot backward, which means that we want to go backward, back propagate, and loss dot this is like back propagating. It automatically computes along the operations. We do not need to manually do this. And optimizer step is which means that we move or update the model weights as per the optimizer. So this is the training, and yeah, so like this is very simple, uh, Timbaland. And this original neural network implementation is very tricky to implement. We have to define all these weights, then compute, then define all these functions for predicting and training. Even and like this, it was when there were the layers were simple and the loss functions are also very friendly. The loss also friendly. No, yeah. So this is for training. This is for testing. Also, we do similar. We generate a data set, make a test loader. We set model.eval. Okay, model.eval means that it will compute, but do not change the gradients or the model weights. Model.eval. Okay, and here also we should do model.train. Sometime so it is yeah. So model.train means model in the training mode, and model.eval means in the evaluation mode. I think this is a mm, used so that like the exact thing I can tell you, like it is used. mm, it will disable dropout, also make batch norm work on the averages computer board. So yeah, okay. Model.eval. Yeah, so model.eval will notify all the layers that you are in eval mode. That way, batch norm and dropout will work in eval mode instead of training mode. So yeah, so I mean that's the use of this. Mm, So yeah, so model.eval is used for like switching off any randomness introduced by dropout or batch normalization and ensure that outputs are deterministic, which means that dropout is basically when we switch off some of the computations in the neural network, and batch normalization we do in training. So these things are switched off. Then we initialize the variables, we disable the gradients, we store that no grad for inputs in data loader. We compute the outputs, we get the predictions, and we add how much is the correct and total samples and incorrect sample. We get the accuracy. So it is very simple to implement a classifier in PyTorch. 16.5%. Okay. So this is the basics of machine learning, and now we will be going for to active learning part. So I'll just be touching some things on the active learning. Okay. Mhm. Mm, Recent is okay. Mm, Stuff. Mm, why? So today we'll be going over very basic approaches. Uh, huh. So uh, not like the today's class was basically to deal with how to make basic classifier model. Now this is for the getting a feel. We'll be getting you should note down the mathematics that I'll be explaining, but if something is not very clear, it's fine. So active learning, basically what we do is hmm, okay. Yeah, this is the one I think. Hmm. So so this is basically uh, what we can do is we can in active learning there are basically two approaches. One is this uncertainty uncertainty modeling, and another is representativeness. So which means that suppose we have lots of data, uncertainty, which means that our model is not performing good on which of the data points, we do select them first. And representativeness, which means that we should perform, like we should find which samples represent most of the sample. For example, it's like you are not performing good on the exam, so there is some you can find those questions which you are not doing good, or you can find practice those questions which are most likely to be appearing in the exams. So representativeness is that. Now we whatever like the approaches, like the ideal approach should combine both aspects. It should have some component of uncertainty, some component of representativeness. So these are some of the methods. One is the least confidence method, this one, which means that you compute the maximum score of the like you got a distribution from the softmax, you find the most probable class, and then you subtract it from 1, which means that if you have say zero point 0.5, zero point 0.4, zero point 0.1, the maximum of these values is 0.5, which is the first 1, you compute difference from 1, and that will give you the confidence. And you have to select the ones with the least confidence. So that is one approach. Margin sampling. Margin sampling is basically when you compute the difference between the most probable and the least probable, which means, okay, I should do it like this. Uh, like screen is visible, right? Mhm. Like you guys can see double screens, right? Hello.
Yes, yes.
Yeah. So uh, I can take example like this is really simple. Suppose the softmax you got is zero point 0.5, zero point 0.4, zero point 0.1. Then confidence will be 1 minus zero point 0.5, the maximum value, which is zero point 0.5. So you take among all the samples, you compute the one with the least confidence. Margin sampling is basically computing the difference between the top two ones, which is zero point 0.1 here, zero point 0.5 minus zero point 0.4. That is margin sampling. Token entropy is basically you for all the samples you compute this. Entropy means p log p. So for all those features you compute p log p value, which means zero point 0.5 into log zero point 0.5 plus zero point 0.4 into log zero point 0.4 plus zero point 0.1 into log zero point 0.1. You sum them up and you do a negative because entropy is defined like this negative function, which means that if you have like if you are a very if the model is very confident about one thing, then this value will be very low, and you sum them over for all and then cases. That is this part is computing token entropy, and these are various formulations for computing token entropy. So yeah, so this is essentially in uncertainty sampling. Uncertainty sampling we studied least confidence and margin sampling, entropy sampling. Now, what we can have is we can have query by committee also. Query by committee, which means that there is a group of models, and in what we can do is we can find the most disagreeable sample. For example, we have three machine learning models. What we can do is find the most model, and this is a formulation for that. So like these are various formulation, but you don't have to go into that depth for that. This is expected gradient length. Expected gradient length is basically one of those models where we try to predict which sample will cause the maximum change in model's parameters. No, no. Yeah, so that one we take. This is the expected gradient length. So these are basically what the information or the uncertainty based models are the. Then we can have representativeness or information based models. Like these models, they kind of optimize some parameter like these confidence sampling and entropy. Then query by committee, which means minimizing the disagreement, which is by different model. Expected gradient length is like minimizing the expected model change. They were all uncertainty based models. Then this is representativeness models, which kind of suggests that how like often a model appears. So you can see that there is a information density. We propose like okay. Uh, so they are not like representativeness models are never used in like alone, because if you can see that suppose there is a distribution of models, then if you sample without any active learning strategy, you will get samples which are higher in proportion, more frequent than the samples which are less frequent. So there is no point in doing active learning, which means suppose our model has the distribution of the cat, say we have cats fif- uh, 80%, dogs are 15%, and un unclassifiable or random variables are 5%. So if you sample from this distribution, 80% time you can get cats, 15% time you can get dogs, and 5% time you will get unclassified. So there's no point of doing active learning. We use these in accordance with other models, like using along with this uncertainty sample. So this is something like you want to practice questions in exam. You will you take a balanced approach. Neither will you waste your time on doing uh, very hard questions. What's wrong with me? Or neither you will not waste your time in doing very hard questions, but you will also practice some questions which are most likely to come. So you'll take a balanced approach. So these information based models are used in accordance with these models. So there is what we do is there is some metric of information, which means which again approximate like how often this sample is likely to appear, and then there is some component of uncertainty in the model which we'll use, and we develop a metric by combining these. So this is active learning basically. So now today I have given you feel of active learning. We'll be dealing with these simple models in detail as well as implement them. Okay, and assignment for this week will be implementing uh, PyTorch classifier on a classification data set. So I'll be sharing the details of that, and like this assignment is very easy. Like you can just simply ask ChatGPT to uh, develop this classifier or something and all. But I want you guys to understand like how this will, because this will become handy when we implement active learning algorithms. So that's all, folks. We can stop recording.
Could you please send this document adaptive learning?
Okay, so I'll share this paper. This is not actually a paper for active learning. I'll share some other paper, a survey for active learning. You can read that. This is for a sequence labeling task. I'll share these two papers. Besides, I'll do is I'll share this PyTorch notebook so that you can get some reference for developing doing the assignment. And I'll also share resources on. There's one thing which came in the middle. Uh, okay, so let me write it down. What I have to share is notebook, paper on AL. I'll share two surveys. These are very long, but you have to just skim it over so that when I tell you, you can relate. Okay, you don't have to like dive too much. If something is not clear, you can ignore that. I can understand uh, like this project was a little bit tough for you guys because I just rushed over all the machine learning parts, which usually people cover itself, do itself in a separate project. So I'll share two papers by Seattle's. These are very good surveys, and I'll share the assignment. Assignment will be ready to be thoughtful of or like study this code well, because assignment will be very easy if you just learn this and implement it. I'll add some constraints as well as share the data set. So that's all for today. Any other doubts? We can stop recording.